For some products, you got to have it because they're sensitive to moisture or heat. Or we have this wet granulating process where we mix powders up, we wet mass, add the pharmaceutical glue, dry, mill, and then final blend and press. So that's our process step, and here's how we do it. So when we determine that pathway, this is a really good slide for you to look at from a standpoint of, is that material directly compressible? Because if I have an API, first question is, can it compress? If the answer is no, I've got to granulate. If it's cohesive, if it's sticky, if it'll hold together, then I might be able to directly compress. If it's not, I have to granulate. Does it flow well? Same thing. How about this acceptable content uniformity? If I can't get the powders to blend without segregating, if it won't work, then I must granulate. So I can simply take this product and look, do I have acceptable bulk density? If I have variations in bulk density where I'm allowing segregation, then I have to granulate. So if I can do all these things successfully, I can directly compress. If I can't, I got to go granulate. And like I said, if material's sensitive to temperature or moisture, then we have to dry granulate. If it's not sensitive to temperature or moisture, I can wet granulate or dry granulate. I can do either. Yes?
What do you characterize fluid bed granulation in your last slide?
Where do I characterize it? Definitely fluid bed granulating, right? So I'm going to granulate or wet mass. I'm adding a solution to the powder. So that would be the wet granulating process. Okay? Good question. So here's my wet granulating process. Weigh the materials, get rid of the lumps. I'm going to do some pre-mixing. I'm going to wet mass. I'm going to dry. I'm going to sieve, and I'm final blend. So what we're going to talk about right here is this section, pre-mixing, wet massing, and drying. So here's a fluid bed suite. Fluid bed granulator over here. It's a little bit dark on the picture, I apologize. Here's the bowl. Here's a person loading that bowl with materials. So they're up on this mezzanine dumping product in. There's a good way to do this and a bad way to do that. Bad way. Anybody know why that's a bad way? If you were there in the room with me, the guy had, every now and then he'd fall in. It's not a good thing. He also didn't have any kind of grounding strap or any way to control discharge, static discharge. And when you get around dust, I think static's a slightly important thing, wouldn't you say, Mr. Freeze? Oh, well, you don't, you're on. Oh. The reason I have Peter standing up to mention something is very important to me. He had an experience that I think you should share.
Yeah. General question is dust, is that your enemy or not?
It's the enemy.
It's the enemy, right? We agree on that. I had the unfortunately experience that I had a dust explosion in my operation. And we've been operating for decades, doing the same stuff like you do. You're filling a blender with powder. And we did that for years and years and years, and one day the whole blender blew up. Moved a few walls around and did a lot of damage. So any type of dust you have is ignitable. You can have an explosion. Everybody knows about the fire triangle. What do you need to make a fire? 3 things. Help me out. Fuel, oxygen, ignition, right? That's all you need. If I got wood, I got the air, and I got a lighter, it's going to burn. On the dust explosion, you have to add 2 things. One is a confined space. So it has to build up somewhere inside a confined space. The other one is a concentration. It has to be the right concentration. If you got those 2 things, it will blow up. And that's why Mike was saying the grouting strap. I mean, we did a lot of investigation, and it came down to a static electricity. So an operator did something and had a static spark going, into the blender, and it blew it up. And all we did was filling ibuprofen into a blender, the raw material of ibuprofen. That's what actually blew up. We were very fortunate that we didn't have any serious injuries, but it could have killed people if they would have been in the wrong spot at that time.
Yeah.
In North Carolina, there was a plant completely blew up. I forgot which one it was. It's about 4 or 5 years ago.
Was that?
Generated a little explosion. They had tiled ceiling, you know, the ceiling tiles. And they've been operating for decades in there, and all the dust was building up on top of the tiles towards the roof. So now you have your confined space right there. You have your confined space between the roof and your tile. So that little explosion they had in the basement generated a pressure wave, got all the particles laying on top of the tiles airborne, and that was like a domino effect. It just went throughout the entire building.
So the powder's laying on top of the tile. It gets elevated.
Elevated.
And
that little
ignites.
fire, that little thing came up and just ignited that dust, and it just went through the entire building.
Wow, so you have a little bit more respect for powder?
Yep. So, I mean, the outcome in my operation was that operators actually had to wear special footwear. They had static dissipating shoes on. And before they could go anywhere into a room where there was powder, they had to step on a platform, make sure that the shoes are working. Everything was grounded to hospital standards, so everything was point earth. That's what they call it. Any differences between one piece of equipment and another, you can have a spark. So, learned a lot about dust explosion. Again, it's one of the experiences you don't want to have, but it's good to have.
Yep. Thank you.
Thank you.
Thank you. Yeah, it's important. This particular guy had a great story. He was telling me one day he was loading the granulator bowl, and he was leaned over like that, and the bowl ignited a flash of flame went shooting around the bowl and then stopped. It didn't go any further. It was just whoosh. But it changed his life. It was pretty interesting to hear the story. Very exciting. Pre-mixing and wet mixing cycles, very important part of the preparation of materials to granulate. I use a picture of two guys struggling to get a bag of granulation out of a drum. I don't know why, it just struck me interesting. I asked them how long they had been trying using that same style drum. They filled the product into the drum. And for 5 years, they were trying to get the product. They'd lay it on the floor and try to shake the product out of the drum. So sometimes we get caught up in not preparing things and not thinking about how we're doing things in the process. So when we're working with stuff, we want to know the bulk density. We want to know the particle size distribution. This is that slide when I started talking about fines. That's very important. And basically, this slide is saying that I don't want anything too big. I don't want any huge granules. And I want 10 to 20% under that 200 mesh. So that leaves our objective of achieving some good range within that to achieve the best possible granulation. That is, if I have a product somewhere in this range, it's going to perform the best. It'll perform well. It'll flow well, compress well, work well. Now, depending on the tablet size, if I'm making a real small tablet, this may shift to the right. I may need a finer granulation. If I'm making a much bigger tablet, then I may need to shift to the left, to a much bigger granulation. And so how I wrote the slide was 3 ways. In mesh size and micron and thousandths of an inch. That's what I did. So 20 mesh is 850 micron is 3 thousandths of an inch. I mean 30 thousandths of an inch. And then 40 to 120, so 425 to 125 micron. That's where our bulk of our product needs to be. And our fines, 200 mesh is roughly 0.0029, which is 3 thousandths of an inch. So that's our goal. Now there are a lot of metrics, Hausner ratio for compressibility. We have, so for the flowability of product. We have the CARS index for compressibility. We have a lot of different things. We don't have time to really go into all the metrics on developing products, but I'll tell you quickly that a lot of these things are guides, that in my opinion, there are not all the tools we need to really generate the data for good product. Let me put it differently. We knew a guy at Eli Lilly named Luther Sutherland, and Luther could reach into a drum of product, squeeze the product, open up his hand and go, it's going to work. And he'd look at that and he'd see how the powder fell off his fingers. And then other days, the whole tech team would take at this product and they'd look at the flow index, they'd look at compressibility, they'd look at every metric that they could get, and they'd say, it's not going to work. And Luther would reach into the drum of product and look at it and go, yeah, it will. And he was right more than they were right. So what does that tell us? It tells us, geez, how predictable are we? So we need to respect those metrics, but they don't always give us all the information that we need. So when we prepare a suspension for granulating, when we're going to wet granulate, we need to prepare a suspension. We need to have, parameters of rate of addition, the temperature of the product, the mix time, having a certain vortex, avoid lumps. We need to have a consistent way to prepare a suspension. And there's good ways to do that. It's all about getting that suspension right. Then when we mix that in, our objective is to simply add a solution into a powder to reach an end point. That is, at what point do we stop mixing is called the end point. And that can be determined a lot of different ways, and we'll get into that here depending on the different machine that we use. How do we measure how much moisture we have is a lot of times a tool called loss on drying, LOD testing, to make sure, see how much moisture we lost to get to our result. How do we know we did a good job? Performance on the machines. If it performs well on the machine, that's the best metric. You can do a lot of testing, but what do we want? What is this right here? Anybody know? Rat hole, pour flow, and that's what this little thing is showing, is as you turn it one way, funnel flow versus mass flow, you're going to see a difference in performance of the granulation, how well it flows, if it segregates, if it works. So that's what we start to look at. Did we granulate or did we overgranulate? Did we undergranulate? What do I mean? What I mean by that is simply you can put powders in the machine, you can spray solution in and not have granulated. That is, you can underwork or not be effective. You can overwork powders to the point where you've overgranulated, and yeah, it's a purple glove. Is that you asking that, John? Yeah. The gloves are big? No. The lumps. Yeah, we granulated well. What do you think? So the reason he's laughing is that what we're trying to do is we're trying to do that in the granulation process, in the wet granulation process, but we're not trying to do it to that extent. We want to build granules. We want powders to be joined together into an agglomerate to control them, but we don't want to build it up to a snowball. And that's what happened here. Their solution was to grind them up and distribute them in the blend. Not a good idea. So let me take a step back here and separate equipment a little bit for you. High energy, medium energy, or low energy types of granulators. For me, I found it best to categorize them this way. So high shear, Littleford, Fielders, Diogenes, Vectors, Glatz, bowl type granulators. You see the one right next to you here? The two units right here? High shear granulators. So different types of granulators, and then medium shear. Let me show you what I mean. So traditionally, one of the most common high shear granulators was a Littleford Lotaget type granulator, a big horizontal piece of machinery, and this machine had big plows in it, And those plows, if you looked at it from the end, you'd have these big sweeps or plows to push powder around to mix the powders. I'd have a motor on the side with a chopper on it. Looked like an outboard motor propeller. And so what that did was that de-agglomerated. That prevented those big balls, the big lumps that you saw from happening. And so when I added solution, that I was mixing the powder and breaking up the agglomerate so I wouldn't have too much agglomerates, too big of a buildup. So the idea of this thing is to have big plows moving around, pump solution in, and break up those any lumps that are too big. Simple objective. Sometimes this process can be controlled very tightly or very closely because of the amount of solution I'm adding. So sometimes I might add a lot of solution to really make a dense granulation, to take powders and really make them almost like I'm making a dough. Other times I could take the same technology and add a little bit of solution, distribute that solution very evenly, and just add enough moisture to make my product more compressible. Depends on what my objective is. In a vertical granulator, which is fundamentally the same thing, it's the same technology that was horizontal, I just turned it this way. I still have the big sweep. I still have this ability to pre-mix or mix the powders well. So before I loaded this, I got rid of the lumps. Then I took my ingredients. Let's say we had 3 ingredients. And I take my ingredients and I may put them in a certain way and then pre-mix, mix the powders up. Then I have some type of spray apparatus to spray the solution onto the powders while they're mixing. And so I'll mix and I'll watch for my endpoint. And my endpoint is how much energy does it take to move that powder. I can watch an amperage gauge, basically, and I can watch that it's taking more and more force to mix that powder. And when it gets to a certain point, I know I've met my end point. It's very simple. And then you see that long nose on the granulator. That's part of our discharge. You can see it here in this picture here. So inside the unit, you see the sweep, you see the chopper. I can see where I add solution through the top. And so I go through my mix, I go through my de-lumping with the blades, and when I've achieved my endpoint, I discharge this powder or this wet mass out and take it to a dryer. So the only thing this is going to do is uniformly put solution into the powder. That's what that's doing. And here's a couple of looks. There's several machines around here. There's a little one in the back that we'll be able to take a look at in a little bit. You can see this is compliments of glad of John Carey that's here today, of different types of granulators that he has. High shear has a great picture here, and right straight in the back another machine that looks just like it, where we have a planetary, more of a little bit lower shear, not quite as high as the other. But what we're looking for is uniformity, to mix well, to make sure we have uniformity, and if we end up with buildup on that in that granulator, we're losing product, we're packing product on the side of the granulator, we have a non-optimized operation. In medium areas, anybody recognize this? A Hobart mixer, make donuts with. We like using it in the kitchen. Great, it's a great mixer. A couple of problems with it: open on top, so I can lose product. Doesn't really mix well top to bottom. It may mix good this way. It may not need the way I want it, but this is traditionally one of the most common machines years ago in the business. When I got into the business, it was very, very common to use a Hobart mixer like this, or something called a Pony, or a Sigma blade mixer, and all those mixers were making dough. They would take the dough and they'd make and wet mass the powders and literally make a dough or heavy granule. Then they'd take that product, that powder or that wetted mass, and they'd spread it out on trays. And we put it on trays and put it into an oven to dry it. And then when it dried to a certain point, we'd take it out and we'd mill it. And we'd check it out, and then we may re-dry some more. We may go through another process step, but that's how we would actually, that's traditionally how granulations were made. Just like you cook in the kitchen. Hobart mixer, wet mass it, and then put it on a tray to dry it. Nowadays, we have more enclosed systems that give us more control especially for tough products to handle, for containment. How they work is very much the same way. I have an impeller, I add a solution, I want to deagglomerate, and I want to control that process. I want to control how fast I mix, what I'm mixing, and how fast I add the solutions. Number of different types of granulators that John's got, that Glad offers, the fluid bed systems. So low energy mixers, V blenders, double cone blenders, fluidized bed granulators, how they work as granulators. If I just take a mixer, a double cone mixer here, inside I have a bar called an intensifier bar that spins at a high rate of speed. And I can pump solution into the bar and create a gap or an aperture and actually have the solution be thrown away from that bar into the powder mass. So I can mix at the same time that I'm throwing solution into my powder mass to granulate. I can actually put a jacket around this blender to dry, or I could discharge the product and take it to a different type of drying mechanism. The fluidized bed system, a little bit different concept completely. A fluidized bed is a great way to take, what it does is what we're trying to do is elevate the powder, to percolate it, to get the powder to move. All right? We're taking the powder, and then as it's there, we're spraying onto the powder. And we're coating the particles and creating agglomerates. So what a high shear granulator does, that we started with, that big mixer, or like the granulators right there, produces a more dense product. A medium shear, kind of in that medium category, doesn't create a really super densified product. In the low shear end, with a tumble blenders or like a fluid bed granulator, we're not making as dense of a product. We're aerating the product and we're spraying and coating onto the particles and then drying at the same time. So 3 different technologies. Some different looks at different types of granulators, and what's very important is the amount of product, the airflow, the air temperature, making sure that our filter system's working properly. We can literally have a 3-day session just on fluidized bed granulating. Would that be fair to say, John? Easy. Just on how to granulate in a fluid bed, or just on how to granulate in any one of these technologies. So what we're trying to do is give you a snapshot that a high shear granulator is to make a dough, to make a wet mass. A medium shear will do it, but not as dense. A fluidized bed system or a V blender or a tumble blender will make a lighter weight, very airy, more of a granule. A lot goes on. We have to premix the powders. We have to have a given spray rate. We have to control the spray. We have to have a given drying pace. And then we have to cool that granulation down. If you take a look down in the bottom right-hand side, that's a spray nozzle. You think that if I think I might have a problem in my granulation if I have a spray nozzle build up a little bit like that? It could, very much. Because what happens is the wetted particles, the wetted powders, get on that spray gun, and this is a spray gun that's in a fluidized bed system, and you can see the top spray arm that's coming across, that you can see it coming across, and it's spraying down on the powders. Well, I've got this air coming up and mixing and moving the powders. If the wetted powders hit that gun, they can block that spray, and I could be spraying non-uniformly. I could stop my perfect atomization and start dripping, and so then I have some wetted product and some non-wetted or drier product, so I could have poor uniformity just because I I didn't have everything in balance. So I really have to keep an eye on watching the spraying conditions and how I do things. Fluid bed is very unique. Fluid bed systems can be used a few different ways. And it's important to talk a little bit about them. That is, what we just talked about is basically a top spray. That basically I can take and mix and move products within a chamber and spray down on top of them. Now I can also not spray it here at all. I can just use the fluid bed as a dryer only. And that's actually a very common thing to do. If I granulate, say I have this granulator here, a high shear granulator, I still need to dry the product. A fluid bed system is a spectacular way to dry. What used to take 24 hours in a tray dryer sometimes takes 1 or 2 hours in a fluid bed dryer. So there's a great advantage to using the fluidized technology to dry a product over what a tray dryer could give you. There's a lot of problems that can happen in equipment, in the process, in the procedure of using the fluid beds, having good cleaning techniques. This particular customer had never ever taken the gun apart. Didn't know how to take the gun apart. So the only way they cleaned was they took the nozzle and they stuck it on the sink like that. And they waited until the water got clear and it was done. And that's a shame. That's not good cleaning. I don't think Carol's ever seen this picture. Can you tell me anything wrong with that picture? It doesn't have...
Well, they're not labeled, so you don't know what it is.
Don't you?
No.
okay.
You don't know what the use is for. It's just, that's bad.
Yeah.
That's bad.
This is a little lab fluid bed. You'll see a couple around here, a couple of different kinds. Spectacular machine to either dry with or granulate with, but it makes a light granulation. So as I get in more into the powders and more in the density of differences of materials, we have to look at that. In the drying process, there's only 3 ways to dry. We can use vacuum to draw off the moisture, use a fluid bed, or use a tray dryer. So a tray dryer is nothing more. Anybody still use tray dryers here? Tray dryers are a great way to do it. And traditionally, old tray dryers, we would actually have to move the trays around because the product on top wouldn't dry, would dry faster than the product on the bottom. So we had to move product around. But mapping of airflow is more efficient now, works a lot better. So newer tray dryers are much superior to older ones. You can get more uniformity in drying. So we have just it's simply nothing more than an oven. A heat system that circulates the air, an exhaust system to get uniformity and dryness throughout the product. Here's a fluidized bed. So it's random distribution of powder, keeps the screen clear and dry, and we want to understand the role of keeping the product moving and keeping the filters from building up with powder. And here's a classic photo of a medium shear wet massing. That is, we're granulating here, moving it to a fluid bed dryer. This is a very, very common methodology in pharmaceutical manufacturing because it dried quickly in a fluid bed. A couple of different pictures of installations. When I got into the business, our fluid bed looked like this box. That was our dryer. It was nothing more than a box that blew air through it, and we had shakers on the socks, and it would literally move the powder around and just dry it and blow the powder around and dry it, and you kept sampling and sampling until you reached your end point. Now, the development of the fluid bed system is much more controlled, much quicker, more uniform, much more predictable than the original ones that we used years ago. A lot of different critical parameters. Sorry to move so quick, but I need to. Let me shift off to dry granulating here. So we kind of buzz through wet granulating. Dry granulating is densification of powders. It can be done 2 ways, either a roller compactor or a tablet press. Here's a picture of just densifying the powders with using big old punches. Just making big diameter, almost like a wafer, and then grinding that powder back up, blending it with other powders, and putting it on the press. Or I can use a roller compactor or chalcinator. That is, I can densify powders by forcing it between two rolls, kind of like making briquettes for a barbecue grill. That is, all I'm trying to do is force powders together, to densify powders, so I can grind them up and produce a powder. So we already established why we want to granulate. What we're doing here is we're using, with a roller compactor, we're using rolls that turn together, that squeeze the powder, that densifies and turns the powder into a ribbon or some kind of a densified shape. And then what we do is we mill it, blend it in with other powders, and off we go. So what's critical in this type of design, there's different types of roll surfaces that mean everything. So what I did was categorize it really quickly for you. Smooth rolls, we use smooth rolls for sticky products. If you have something that really sticks easily, and you use a cup roll or serrated roll or something with a lot of ridges on it, the product will build up and stick on them and won't work well. So with sticky products, I have to use a smooth roll. With non-sticky or compactable products, I can use grooves. I can use pockets. With axial grooves that are going around instead of radial grooves and axial grooves for powders that are really fluidized easily, are really light and fluffy. So I have to use different rolls for different products. And when we look at the chalcinators or roller compactors here, you'll look at the roll surface to see what those rolls are for. Fundamentally, how they work is, it's pretty simple. We have two rolls moving together and we're squeezing the powder together. Powders don't want to move in between those rolls, so we have to control the feed rate of the powder by using a screw to push the powder down in. And it's first, as we push powder in, there's a region where it slips, and then there's a region where it actually grabs and we have traction and we compress the powders. That's where we're controlling the density of the powder. So what really is important here is this downward force. The control of how we control the flow of the product becomes critical to the uniformity or success. Yes?
There are different vendors or suppliers for roller compactors that use different angles for input. So you have some that come from the top, you have some that come from the side.
Yeah.
Some from the horizontal.
Very
What
good.
impact does that have?
A great deal when it comes to, let me just finish these two slides and I think I have an answer for you. So just to categorize roller compactors, they come in all sizes, just like fluid beds, just like these granulators you see here, small to much larger and higher outputs. And here's a picture of one that's set up in a mezzanine. So I have a roller compactor, I go through a mill, I go through a screener, I can recycle the fines back into the unit, I can re-densify those and go back through, and I can have a very categorized, very controlled end product. Okay, so the question was, some roller compactors are vertical, some are horizontal, and this one's kind of in between. And the reason, you recognize that? It's a Gertis, yeah. The reason for it is one of the toughest things about roller compacting is getting the air out. If you ever compress powders, or when you're making a tablet, I mean, that's our objective, is to squeeze the particles together. So if I've got rolls that cup and grab air, I'm compressing air. And so if I'm using rolls that have a cup in them, if I tilt the rolls or put them over here, I have better air release than I do if I'm straight up like this and I captivate the air. Anybody that's been around a roller compactor a little bit, when you work with a certain product that catches a lot of air, I mean, it's bang, bang, bang. You really hear that thing releasing because of the air, the amount of pressure as a result of the air. So the reason for the design, to answer your question, is the reason that we put one on horizontal axis or tilted a little bit is to control that cavitation that goes on. The other way to control it is to add vacuum, to put vacuum and to draw the air out of the powder. That's the only other way to do it. But it's difficult because if you look at these, they're open systems, so it's really hard to really control that vacuum really well. That answer?
When you said the banging, that was the cavitation of the rollers moving?
Yeah, actually, yeah. So if you look here, this is really a good one because what this is showing is here's your two rolls. These are the drive gears out here. So I have a fixed roll and I have a floating roll. The objective of the roller compactor is to press to density. So the minute my product is more or less dense, you know, it kind of moves. So if I all of a sudden compress air is a lot harder to compress than the powder itself. If I start compressing air, then that forces that roll apart and you start to hear this. Bang, bang. Yeah? You look confused by...
Oh, I thought air was compressible.
Air is compressible, not as compressible as powder.
But you'll see the two rollers separating back and forth.
You'll see one of the rolls, the one's fixed.
Yep.
Yeah, and the other one will be moving, absolutely, because the objective of this machine is to control density. So you want to set it, so one of the options for the lot of roller compactors is to have vacuum, to add that on. To add pre-braking, nitrogen blanking, or cooling conditions for materials that are sensitive to sticking or buildup is important as well. So if you look inside, there's a horizontal screw bringing product to the machine and this downward screw that's bringing product in between the rolls. And that's the most important part besides the roll surface, is making sure I'm delivering powder as uniformly as possible. If I don't do that, then I will not have a good end result. And there's a lot of people who chalconate and you end up with powder that's not any more uniform than when you started because they weren't driving the powder into the rolls at a proper rate. It becomes very critical.
Why do you call it chalconing?
Because it's a mistake on my part. Fitzpatrick coined the term chalconation, the Fitzpatrick Company, and so that's their terminology for roller compaction is chalconation. So the generic term is roller compaction. The brand term is for Fitzpatrick is chalconation. But I make that mistake, and as a lot of people do in our industry, that I typically, you know, a lot of times use, say, chalconation and roller compaction interchangeably. But it's chalconation is really Fitzpatrick's. Mm-hmm. Was there a hand up? No? Okay, so summary. The objective again was to improve flow, compressibility, density, to achieve those attributes and to get that result at the tablet press, to get the best possible tablet we can get. That's a lot of information very fast, isn't it? Yes?
Something I didn't get clear on, maybe I missed something you said. Explain to me again the deaeration on the compaction, on the roller compactor. If
Okay.
you don't have vacuum, say
Right, okay.
deaerate.
When we walk over to a roller compactor, when you look at a roller compactor, I think maybe this is the best way to do it. So in this picture, you see two rolls moving opposite direction, right? Pushing the powder down. So if I have, based on my roll surface, if I have a lot of air within my powder, if I don't squeeze or push that air out and I start to compress air because of the surface of my roll may have little cups in it. So I start to compress that. Air is much harder to compress than powder. And what will happen is that air will cause the roll to release at the tonnage it's supposed to release, and then it's not densifying my powder to where it needs to be densified to.
So, what I'm asking is, where does the air come out? If you don't have a vacuum capability,
Oh, yeah,
does it come out because of the vertical screw, or where?
right.
Where do you lose the air as compared to
Where is it vented at? Right, yeah. And so it's vented a couple of different ways. I can relieve the roll, or it's simply a release between the powder and the roll surface itself. It is not a directional, there's not a specific direction of release. It's just that what happens is it moves the roll out of the way. The compression of the air gets to a certain point and that roll moves.
Or let me rephrase the question, how do you avoid that happening? In other words, how does someone who's doing this
Great. Right, right.
get the air out, or is it just vacuum, you have to have vacuum?
You don't have to have vacuum. The ways you're going to control that are two ways. One is controlling the rate of powder that's coming into it. The more you force the powder in, the more you pre-force air out of the powder to begin with. If you're bringing the powder in too slowly and you captivate more air in the powder, then you're going to have more cavitation as a result of not pushing the air out of the powder to begin with the screw, the top screw coming down. That's one way. The other way is speed. If you slow the rolls down, then you're squeezing the powders and the air can move out more slowly. Whereas if you increase the speed, you're more likely to captivate the air and the air can't release, and then the rolls separate. So if you don't have vacuum, you have to really control your screw feed rate, and you have to slow down your rolls. Yeah, thanks.
You increase the speed of your feed hopper screw, or the screw into the rolls?
This speed here and the flow in between the two rolls is my most important feed rate. I simply need to bring powder into this screw to deliver it at a good uniform rate. But the downward flow between the rolls is what becomes very, very critical. And these are great questions, because this is exactly what happens. Is a lot of times I'll go on the floor and I'll hear bang, bang. I'll really hear these rolls moving apart. Okay, first thing I do is slow it down. So it gives two things happen. When I slow it down, three things happen. When I slow it down, I'm giving air more time to move out, but I'm also, because the screw was turning not at the right speed, it's actually pushing more powder down because the rolls are moving slower. And the third thing that happens is my boss comes and yells at me because I just slowed the machine down. So to make my boss happy, I'm not supposed to slow the rolls down. I'm supposed to control my horizontal and my vertical feed rate, but the most important one is making sure that I'm pushing the powder as uniformly as possible in between those two rolls. And that little picture that I just showed you is really an important one for both air and for density control, is that as you're pushing powder down, you can only get that screw so close to the rolls. So then you have a region of where the powder is just sitting there. I need to be pushing on the powder so the powder pushes itself between the rolls, so I grab it. And the grab area is the nip region, and that's where I'm squeezing the powders. Yeah? Okay. It's lunchtime. Thank you very much. What's the plan on lunch here? Oh, sure. Yeah, no problem at all. Okay, I'm sorry. I thought you were anxiously awaiting. Okay. I'm sorry, I misunderstood. I thought I was 15 minutes late, Adam. I was... Okay. Okay. Okay, so let's move on. Let's talk a little bit about blending then. Let's move on to the next section here, and we'll start blending, and we'll go back and take a look at equipment in a little bit here. So blending of powders is a whole different thing than granulating. Getting powders blended and meeting the objectives of putting powders together is a very important thing. We have to make sure that we know what the characteristics of those powders are, as we already established, and we need to know a little bit about that, what we've been talking about bulk density wise. So let me look at this again, bulk, and specifically identify, when I talk about bulk density, this is what I mean, that I've got right here, I've got 5 different beakers. Each one of these weighs the same amount. So the powder in each one of these is equal. So this powder would be considered fluffy. Is that a technical term? Fluffy versus extremely dense. So how would I hold those powders together? If this was my blend, could I make any prediction about how well it's going to perform? If I just blended these powders together, do you think I'd have good weight control on my press? Do you think I'd have good predictability on my machines? No, because there's too much difference in the density of particles from here to here. So my objective is, this is when I have to stop and go, hey, I should have granulated. I should have roller compacted. I should take the light fluffy powder and densified it some way, either roller compact it or granulate it. But I need to take these things and make them all more equal. Is really what I need to do. Now, sometimes I can take sticky materials or coat different products and make them work. But most of the time when I have this big of disparity, the only choice I have is to granulate. So if I was just trying to blend these, I probably couldn't do it. So that's when we're talking about bulk density and we're talking about trying to get products to stay together, that's what we're referring to. And when I talk about blend uniformity and the result on the press, this is a picture of a punch. And what I'm trying to achieve with blending is I'm trying to make sure that the powders are performing the way they are and not separating or segregating. If I showed you this station of tools on the machine, the lower has all this buildup, frosty looking, actually product is sticking to the face of this tool. If I showed you the upper punch, it was perfectly clean, shiny. So if I have a shiny upper and the bottom was shiny to begin with, what does that tell me that the powder's doing? The powder's separating as the die is filling. The heavier particles are falling down and the lighter particles are floating to the top. And when I compress them, there's proof. And this is the reason that I handed this out, because this really shows you the same thing. If you take this and you just turn it on the side a little bit and shake it, and as you shake that, you're going to see that one side is pretty light, and the other side is all the darker, heavier product. So that's exactly what's happening, can happen on the machine, is that as the powder flows through the machine, as it transfers, I have a completely non-uniform. One side, the lighter product moved to the top, the heavier product moved to the bottom. That'll actually happen as the die is being filled. And in this particular case, it's proving it. It's saying, look, the product is sticking to the tool, but it wasn't sticking to the upper. So it proves that there's some segregation going on as that die is being filled. So how do I correct the problem? I have two big disparities. I have superfine particles and a bunch of bigger, heavier particles that are separating when I'm filling, and I got to do something to control that. It has nothing to do with the press operation. You can polish punches until you're blue in the face. That doesn't fix the problem. And that's usually the solution that most companies go to is, oh, the punches are sticking, let's polish the punches. But they're not solving the problem because the granulation is actually segregated. So a good, easy rule to understand here is very simple. If it's sticking on the bottom punch, that's a formula or a process problem, a granulation problem. If it's sticking on the upper, it might be your machine operation, might be your setup, it may be the granulation. But if it's sticking on the bottom, that points directly to your formula. That points directly to your process. There's a lot that goes on in blending with variability, particle size, distribution, shape, stickiness, cohesivity, surface coating, particle interaction, static charges that we talked about. There's a lot that goes on with powder preparation of pre-blending, for granulation, or final blending after we granulated. All of these attributes contribute to whether we're going to have successful or non-successful blending. So when we get lumps, we only have lumps for 3 reasons. Whether it's in the material to begin with, it comes from bad or no screening, from static electricity, or from moisture. That's the only 3 reasons we have them, and we need to control them. So we need to control many, many factors to have success in blending. Flow rate of the material, the compaction condition, vibration, temperature, humidity, electrical charges, aeration, all of these things contribute to that success. So the reasons to blend, or reasons for blend testing, is to optimize the time, to demonstrate segregation, and to confirm that specified blend conditions produce acceptable uniformity. That is, our objective is simple. We need to blend powders to achieve the most uniformity we can in the shortest period of time without causing problems to the product. Some products are naturally sticky, and some products are naturally friable, break down. So we have to recognize the characteristics of those powders and see how we're going to more successfully work these powders together. If I have a product that's friable, what does that mean? A friable product means that as it rubs against itself, it's going to break down more. So if I have overblend, or long blend times, or a slower blender, or a blender with some kind of an intensifier bar that could beat the product up, I can break those particles down. If I have sticky products, I got to be very careful of not generating heat. So I'm basing my blend characteristics and my blend time on the characteristics of the powders. It's not simply, well, Mike said turn on the blender for 3 minutes. The prediction, I can't predict what your particle characteristics are.
Can you go one back, Mike?
Oh, sure.
That's the one. Just want to ask a question. There's 2 things on here where Mike really didn't get too far into it, which is transportation, storage time.
Can't hear you, Peter.
Can't hear me?
Well, that's not a speaker. That's just a recorder. So just you have to talk louder.
Okay, I can talk loud. All right, talk about transportation, talk about storage time. How many of you guys are actually doing a what's called a blend hold time? Or you heard about that? A few, right? You wouldn't believe how your blend is changing from the time you discharge it out of the blender until the time comes you're going to take it from the warehouse and bring it back. It needs to be compressed. A lot of you guys, if you watch the powder coming out of the blender, it acts like water. I mean, it's fluid. I mean, the whole thing is like going like water. You get it into the warehouse, you're going to lose a lot of air already at that point. But then if you got an extended time frame between the finishing of the blending going into compression, that powder is a totally different animal than it was in the beginning. And a lot of times the process is that sometimes it's only a couple of days until I compress, and sometimes it's a couple of weeks. And then people say, and they call us for that, my powder runs sometimes, and sometimes I can't make any towers. And then you go into the troubleshooting, you say, hey, this is where your problems are. And it's the storage environment. You can have a really nice controlled area where you actually manufacture things, But how about your warehouse? So if you come out of your manufacturing area and you store it in a warehouse where there is no humidity control, no temperature control, you're going to have your blend also being a totally different blend than it was inside your manufacturing area. Just wanted to emphasize a little bit on that one.
Yeah, that's great.
Thanks.
Yeah, I mean it's very true, because what to emphasize what he just said, we were in a facility, and the new manager came in and he literally had a room this size, and the last time we were there, the room was empty, everything was moving through pretty well. The next time I stopped there, the new manager had all blending done in advance, so this entire room was full of blend. So that meant, I said, well, how long until that barrel gets blended back there compared to this one? He said, oh, we won't be blending those for a couple of months. I mean, compressing those for a couple of months. So what Peter's saying is exactly true, that there's a window of opportunity. I can blend too early, or I can leave that product sit and it'll deaerate, separate, segregate. There'll be a number of problems that show up on the press. And I refer to it as kind of like having fresh bread or baking fresh bread. If I said to you, hey, I made some fresh bread 2 weeks ago, how would you like some? You'd say, wait a minute, it's 2 weeks old, it's not going to work. And that's the same thing with powders. And I'm pretty sure that that's exactly what Peter's saying. Okay, so there's two different situations. We're looking at powder flow and processing. And as I go through this, we'll talk about what we're after. We want the ability for products to perform and to perform well. Here I've got a couple of basic types of equipment, and it depends on the nature of the actives on how I use it. Here's an antique, old, horrible looking V blender. Will it do the job? Yeah. How are my GMPs? Not very good. Here's a different type of blender with a loading device, and I can have, so all machines just don't work the same way. All machines are not created equal. So the take-home message is that I need to understand my equipment, and I need to understand the characteristics of my powders. That's all I'm trying to drive apart here. So I have two different objectives. I'm going to blend powders, and I'm going to blend lubricant. In other words, in the process of making stuff, I'm going to have a blend time to pre-blend my materials, and I'm going to have a final blend. A final blend means how long am I mixing in the lubricant? That's the last and final step. The pre-blend, or the blending upstream, is critical as well, is to marry all the products together with my right order of addition to achieve my final content uniformity and my final blend. I don't want to confuse the two issues. They're two separate, completely separate issues, to blend powders and to final blend. So when I'm achieving a uniform blend, materials are going from an unmixed state to a mixed state. And what happens in a blender becomes very important, because how long I mix for and how much product is in the blender are two very critical parameters. That the amount of material in the blender, as an example, if I have a 10 cubic foot blender, and usually a 10 cubic foot blender is referred to in working capacity. So that means there's 10 cubic feet of product in the blender of volume, and I'm going to blend that product. If I change the amount of powder in that blender by more than 10%, I can change, that changes my blend time, how long that blender's on, significantly. There's a lot of studies about this, that if I change the amount of powder, if I increase the level of powder or decrease the level of powder in that blender and turn that blender on for the same amount of time, I'm not going to have the same blend. That's kind of the point, and that's a big driving factor for a lot of materials, that how much is in there to achieve a homogeneous blend is what I'm trying to get through. Make sense? Yep. So we want to study that. And so in my blend, and this is, I've swiped this from an effusivity study, and effusivity is a device that measures blend uniformity by looking at product temperature. What it basically means is that if you're, while you're sitting at your desk, if you put your hand on the table and you put your hand on the book, they're both the same temperature, but they both feel like they're different temperatures. So an effusivity sensor is basically has the ability to mirror or look as an extreme temperature sensitive sensing device that says, hey, I can see that you've got different powders in here, and I can see when they come together and when they move apart. So it's a sensor that's put onto the blender in different places, and they turn the blender on. And there's other ways to do this, not just with effusivity, but we turn the blender on and we watch the particles blend together, and how long can we blend before they start to blend apart. So we can start the blender, and in this particular screen here, it basically says that at the beginning, I've got these components that are not blended well. And as I start to turn the blender on, they come together. They're getting better and better. At about 10 minutes, they're looking pretty good. At about 15 minutes, they're looking like they're pretty optimum. And if I blend a little bit longer, they're moving apart. So whether you have an effusivity sensor or not doesn't matter. That's traditionally how we blend, is by time. So traditionally, when we turn on a blender, we blend and say we're going to blend this product for so long because we've tested it. We've put the powders in the blender, turned the blender on, and said at this certain point we've achieved our blend. So all that I'm trying to point out is that there are variables to that. If there's a moisture change, temperature change,